Let's discuss epoxide ring opening reactions, and I hope that I will convince you that this is a great synthetic tool because it allows us to add some carbons to a chain, and we end up with an alcohol functional group afterwards. And one of the reasons this is a relatively easy thing to do is because of the high ring strain that we see in a generic epoxide, right? This is a 3-membered ring. It is certainly more strained than a 4, 5, or 6-membered ring, and thus it's easier to pop this ring open and relieve that ring strain. So let's look at reactions where we have a strong nucleophile. And let's use NaOH as our nucleophile. We'll do this in water solvent. This is the conjugate acid of the strong base, so it's reasonable to do this in water. And we can use our nucleophile basically in an SN2 reaction. We're going to relieve the ring strain, and we end up with a situation that looks like this. And then we can protonate using our solvent to regenerate our nucleophile, the strong base. And the end result is that I've taken my nucleophile and I've added these 2 carbons and an OH to that nucleophile. So whatever the nucleophile is, I've added 2 carbons and an OH. So there's my synthetic utility. And this is now how we can predict the product that we might expect. So we can also use RO- instead of HO-. We could use CN-. We could use SH-. We could use a Grignard. So here we can add just a simple carbon chain. We can even use lithium aluminum hydride to add a hydrogen. So here we're adding R, and then of course the other ones is evident, we're adding RO, CN, or SH. So you can use a variety of nucleophiles, and we're going to ring open the reaction just like this mechanism I just showed you. Let's look at this reaction if we had a slightly more exciting epoxide. So let's put a few other groups here. I'm going to give a chirality center on the right side. And I'm going to use, in this case, let's use a Grignard, propyl Grignard. So in this case, strong nucleophile. We're going to attack the less hindered side. Okay, so I could draw my mechanism like this. Again, this is an SN2 style nucleophilic attack. And I pop the ring open, so that's the loss of leaving group, of course, just like SN2. And then I can draw the product. And in this case, I have 3 carbons as part of my epoxide. So if I look at my epoxide having this structure here, let me put the minus charge here. All of that, including the methyl that I forgot to add, is part of my epoxide, and then I added the 3-carbon propyl group right here. So hopefully you're starting to get an idea of how we can add groups to our epoxide, end up with a much more complex material. And then the second step in these reactions, since we're dealing with a really strong base, we often have a stepwise reaction, and the second step then is addition of water so that we can protonate and end up with a neutral alcohol product. Alright, and so this is SN2. We did get inversion here. You'll notice that I pushed the methyl group up, and I showed the inversion with my new stereo center right there. So again, the nucleophile attacks the less hindered side, and that's going to be always the case with a strong base. We'll always attack the less hindered side, either the primary side or the secondary side. Let's look at what happens when we have a acid catalyzed. So in the acid catalyzed ring opening, we have a slightly different mechanism. As you might expect with a strong acid present, the first thing we're going to do is protonate, just like we learned with other reactions that involve strong acids. So this is a proton transfer in our first step. So now we have a protonated epoxide, and we have the chloride anion from our strong acid. So now we have a better electrophile. That's what protonation does, and we're going to see that theme many times in second semester organic chemistry. And so now I have a better electrophile. I can take my nucleophile, the chloride. It's not the best nucleophile, but since my electrophile is really quite reactive, this reaction is not a problem. And I end up with this species here. Again, you can see that the 2 carbons and the O are added to my nucleophile, whatever that nucleophile has to be. So again, I'm extending a carbon chain. If I started with a carbon chain, I end up with an OH on the end of a carbon chain. This is a very useful reaction. So I could have done the same thing, and I could have reacted this with just catalytic acid and ROH, so any alcohol I wanted, and I would have ended up with, I hope you're catching on here, I would have ended up with an OR group on the 2 carbon chain bearing the alcohol. So I could also use H2O if I wanted to, and in this case I would get an H right there instead of an R group. So the next question is, what is the regiochemistry of this acid catalyzed ring opening? We can look at a couple examples. So if there's no tertiary site, let's just use HCl. I've showed you the mechanism for that. We're going to attack the less hindered. And so we would end up with that after our HCl is added to this epoxide. Same mechanism as before. We're going to attack the less hindered side because it's more open to attack. What if we had a tertiary side? Let's look at this simple alkene. So let's outline this in red because that's the distinction here. If there is a tertiary, we're going to attack the tertiary site. And thus our ring-opened product will look like this. And of course we'd get inversion at this stereocenter if there was a stereocenter, just like we got inversion at that stereocenter. And so why do we have this different regiochemistry? Well, let's look at the intermediate here. We're going to protonate the epoxide, and we can expect small partial positive charges at these 2 carbons adjacent to the O. And we can look at these partial charges and decide that since the 1 is on a tertiary, it's much more likely that that side has a larger partial positive charge. And so we can model the epoxide to look something like this, where I have a small delta plus here and a larger delta plus on the tertiary side because that's more stable. We know that tertiary carbocations are more stable than secondary or primary. And so this epoxide is set up to receive the nucleophile, and of course the nucleophile should be attracted more to the larger partial positive than the other side. And so only on a tertiary do we attack the tertiary, the more hindered side, because that has the greater partial positive. When we don't have a tertiary, such as in this case, there isn't as much a difference in the partial positive sizes, and that's where sterics takes precedent. We'll attack the less hindered side. Okay, let's look at a few examples here. You might encounter these as a predict the product, and so we need to evaluate the type of epoxide, what conditions we're in, and where we might expect the attack to occur. So let's look at the first one. This is sodium sulfide, and we know that that is SH minus, and so that's going to be basic conditions. And so we're going to attack at the less hindered side. And so that's going to be ring opening at that position. And so let's just redraw the epoxide over here, SH, and let's assume that we're in some solvent that allows us to have some access to hydrogen, so this gets protonated. But you see, of course, that the nucleophile got added to the less hindered side. So that's how we'd predict the product in this case. There's just one product here. We're not going to do anything with this stereo center, so it remains in that configuration that it was at the beginning of the reaction. Let's look at the second reaction. Here we see that we have acid catalyst, we've got a weak nucleophile, so these are acidic conditions. Do we have a tertiary site? That's the question we ask ourselves. Tertiary? Yes, we do have a tertiary site, so that is the side our nucleophile will add to. And so we can draw our product again. The OH here, and our nucleophile is a 2-carbon alcohol, and then we would show inversion of that stereo center, keeping the isopropyl on the wedge but flipping it up, and keeping the methyl on the dash. And so here again we have added to the tertiary side exclusively, and that's what we're going to use to predict the Regio chemistry. If we had a epoxide that looked like this, I'm going to modify this by removing the methyl group. I'm going to use the same reagents as I used in the second example, but now, of course, as we talked about, we get a different regioisomer because the partial positive isn't as large of a difference on these two carbons here. So we're going to get a nucleophile that adds to the less hindered side, and this would be our product because there is no tertiary site. So we add to the less hindered.